And for more NASA videos, hit subscribe.
Between 1968 and 1972, America launched 9 human missions to the moon, 6 of which successfully touched down, allowing 12 men to walk on the lunar surface. NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Everything is designed and tested with our most important element in mind, the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. And a launch abort system, with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there was no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely.
The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the moon days later.
Once this burn is complete, the upper stage of the SLS is jettisoned and the crew aboard Orion coast for several days toward all that awaits them at the moon. Approaching the moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach: pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit, and once again to sling the spacecraft around the moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released, and the crew module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our moon and prove that together we are ready to go beyond.
अब कोका कोला की 2 लीटर बॉटल सिर्फ 220 रुपए में। खाना बनाए मैजिकल कोका कोला के साथ।
सस्ता शैम्पू लगाओगे तो सर झुकाते रह जाओगे। ले आओ हेड एंड शोल्डर्स जो जड़ तक जाए ताकि डैंड्रफ वापस ना आए। हेड एंड शोल्डर्स, अब झुका के नहीं, सर उठा के।
The Holocene has ended. What we do now and in the next few years will profoundly affect the next few thousand years. The only conditions modern humans have ever known so far are changing, and changing fast.
Nothing stays the same on this planet. Everything changes. The Earth is going into one of these jumps, and you don't know what is going to be on the other side of those jumps. The Earth is always jumping. Things move on this planet. Things are not still. Everything is turning.
As it begins to run out of fuel, the sun won't simply fade away to nothing. Its core will collapse, and the extra heat this generates will cause its outer layers to expand. The sun is now dead. Its remains slowly cooling in the freezing temperatures of deep space. The fate of the sun is the same as for all stars. One day they must all eventually die, and the cosmos will be plunged into eternal night.
All stars eventually will run out of fuel. The temperature of the universe drops. The stars, one by one, in the night sky, will turn off. and there'd be no more new stars created. And so that the universe will end not with a bang, but with a whimper. And not in fire, but in ice.
With no fuel left to burn, a white dwarf's faint glow comes from the last residual heat from its extinguished furnace. Looking at it from where the Earth is now, it would only generate the same amount of light as the full moon on a clear night. The faint glow of white dwarfs will provide the only illumination in a dark and empty void littered with dead stars and black holes.
In some ways, it's kind of a ghost universe. It's the corpses, the zombie stars, that will take us into the future.
A black dwarf will be the final fate of those last stars, white dwarfs that have become so cold that they barely emit any more heat or light. Black dwarfs are dark, dense, decaying balls of degenerate matter, little more than the ashes of stars. Their constituent atoms are so severely crushed that black dwarfs are 1,000,000 times
We have a pace of life that's based on really the energy available to us now. You could imagine living conscious systems which have a very different pace and therefore can extend out at least a lot farther than you'd imagine otherwise. You could have a living system where if it had a thought every 10 trillion years, that would seem normal. Even if our life dies out, one could imagine at some time arbitrarily far in the future, a fluctuation occurs which allows intelligent life to exist again for a little while. So you might have islands in time of intelligence.
Proton, one of the fundamental building blocks of atomic matter, of what makes us up, can just spontaneously fall apart.
Any material that evades the pull of a black hole eventually dies away as its protons disintegrate.
The matter inside black dwarfs, the last matter in the universe, will eventually evaporate away and be carried off into the void as radiation, leaving absolutely nothing behind. With the black dwarfs gone, there won't be a single atom of matter left. All that will remain of our once rich cosmos will be particles of light and black holes.
Pond's Bright Beauty Face Wash. Miracles happen.
Seven Up presents Pakistan ka food scene.
The arrow of time creates a bright window in the universe's adolescence, during which life is possible. But it's a window that doesn't stay open for long. As a fraction of the lifespan of the universe, as measured from its beginning to the evaporation of the last black hole, life, as we know it, is only possible for 1,000th of a billion billionth of a percent.
Black holes become the fundamental building block of the universe. A galaxy will basically be a supermassive black hole in a center with smaller black holes orbiting it.
Zombie galaxies filled with black holes continue to evolve.
They'll each other and they'll get bigger, and maybe they'll fall into the supermassive black hole and it'll get bigger. The universe will still be an exciting, dynamic place. It's just that the timescales you're talking about are now trillions of years instead of thousands or millions of years.
Space-time like mallets on a drum. And they have a very characteristic song. Imagine two black holes that have lived a long life together. At the end of their lives, they're going around each other, crossing thousands of kilometers in a fraction of a second. As they do so, they leave behind in their wake a ringing of space, an actual wave on space-time. Space squeezes and stretches as it emanates out from these black holes banging on the universe. Those are the gravitational waves. They are literally the sounds of space ringing. And they will travel out from these black holes at the speed of light as they ring down and coalesce to one spinning, quiet black hole. If you were standing near enough, your ear would resonate with the squeezing and stretching of space. You would literally hear the sound. Imagine a lighter black hole falling into a very heavy black hole. The sound you're hearing is a light black hole banging on space each time it gets close. As it falls in, it gets faster and it gets louder.
Scientists used to think black holes were immortal, but even these one day die.
Now we're talking about timescales of unimaginable length, quadrillions of years into the future. On that timescale, even the black holes begin to evaporate.
According to quantum mechanics, space is filled with virtual particles, nanoparticles, that are constantly materializing in pairs, separating, coming together again, and annihilating each other. In the presence of a black hole, one member of a pair of virtual particles may fall and they vanish in a gigantic explosion. Quantum mechanics has allowed particles and radiation to escape from the ultimate prison, a black hole.
Philosophers and poets have asked the question, will the world end in fire or ice? We can now give an answer. The latest evidence shows that the universe is not slowing down, but it's speeding up out of control. And the universe, we think, will die in ice. Trillions upon trillions of years from now.
Empty space itself has energy, and every little cubic centimeter of space, whether or not there's stuff, whether or not there's particles, matter, radiation, or whatever, there is still energy, even in the space itself. And this energy, according to Einstein, exerts a push on the universe.
What is the weird stuff that's accelerating the universe? We call it dark energy. And this stuff is the dominant stuff of the universe. Almost 3/4 of the matter-energy content of the universe is this dark energy. And we don't know what it is.
Dark energy, unlike matter or radiation, does not dilute away as the universe expands. This has crucial implications for what the universe is going to do in the future.
So what will be the future of the universe? Well, if the dark energy remains dominant and repulsive, the universe will expand forever. Faster and faster and faster with time. A runaway universe.
70% of the energy of the universe resides in empty space, and we don't understand why. But we do know what will happen if that energy continues to be there. The universe will become cold and dark and empty. That's the future as it might be. We don't know because we don't yet understand the nature of dark energy. Until we do, we won't know the future. We won't even understand our own origins, and that's why we want to know and study this subject.
Experience the artistry of Biscone Prime, where indulgence is perfected.
Forecast does seem to be for an ever colder, ever emptier universe. But then, of course, we have to ask, could that end lead to a new beginning? And there are ideas whereby what actually is the end of our universe could in some sense be linked to the beginning of a new one.
We've worked out the mathematics, the equations. They seem to say that if you have an atom smasher that can concentrate tremendous amounts of energy at a single point, you can perhaps open up a gateway, a baby universe. Facing the death of everything there is, this perhaps is their only possibility of escape. And this also raises a very intriguing possibility, sheer speculation of course, that perhaps any universe that has intelligent life in it will create baby universes, will create lifeboats, and proliferate child universes. So an evolution may take among universes in the multiverse. Survival of the fittest may take place. So those universes which do not have intelligent life are infertile. They have no children. But those universes that have mild temperatures, stars like us, would create civilizations that could open up child universes, and they would then proliferate.
After an unimaginable length of time, even the black holes will have evaporated, and the universe will be nothing but a sea of photons gradually tending towards the same temperature as the expansion of the universe cools them towards absolute zero. Once the very last remnants of the very last stars have finally decayed away to nothing, and everything reaches the same temperature, the story of the universe finally comes to an end. For the first time in its life, the universe will be permanent and unchanging. Entropy finally stops increasing because the cosmos cannot get any more disordered. Nothing happens, and it keeps not happening forever.
most complex object known in the universe is the human brain. These 86 billion neurons have given us the power to transform our planet. But is this the best nature can do? We now know there are something like 10 billion trillion habitable planets in the universe. 10 billion trillion chances for the brain to be eclipsed by something else. The search for intelligent life is more than just a scientific curiosity. It's driven by a deep desire to connect with something greater. Finding an alien civilization wouldn't just reveal we're not alone. It could chart a new course of evolution for our species. And unlike primitive life, alien intelligence could be detectable thousands of light years away, making them potentially easier to find. What do they know that we don't? And how do we make contact? We're not the first to wonder. Years ago, we dreamed of lighting huge rings of fire in the Sahara Desert to signal our presence. And in the 1860s, a French poet proposed a patchwork of giant mirrors, reflecting sunlight to Mars in the form of the Big Dipper. But if you want to send a signal across an ocean of space, bonfires and reflected sunlight won't help you much. Even a nuclear war on a nearby planet would be virtually impossible to detect with current technology. To really get your message across, you need a form of light you can't even see. Radio waves are ideal for carrying information long distance, because compared to other forms of light, they travel more freely through interstellar gas and dust. That's why SETI, the search for extraterrestrial intelligence, has focused almost entirely on scanning for radio signals, whether intentional messages or byproducts of technology. Our own radio transmissions have now traveled 100 light years and reached 75 star systems, some of which include potentially habitable planets. And if alien intelligence lies beyond this bubble of signals, they could still infer life on Earth by spotting oxygen in our atmosphere. Thanks to the SETI Institute and the recent Breakthrough Listen project, we have now scanned tens of millions of stars for signals. But despite all this, after 6 decades of searching, nothing. Only a series of false alarms and dead-end leads. We call it the Great Silence. But in reality, the search has barely even begun. There are 2 trillion other galaxies out there that are still too far away for practical study. If space were the size of all Earth's oceans, we would have searched less than a pool's worth of water for signs of intelligent life. top of this, we might even be looking for the wrong thing. There's more than one way to communicate across space. An alien life might view radio as primitive technology. We have to consider every possible alternative, from the practical to the unimaginable. The search is now underway for a different type of signal, one we could even spot with the naked eye: laser light. High-powered laser bursts can outshine a star by thousands of times and can carry far more data per second than radio. We would have to be in direct line of sight to detect the beam. But spread across many light years, they would widen to encompass entire planets and moons. Fleets of laser beacons could be used to sweep the entire galaxy, like alien lighthouses in a cosmic sea. Thanks to a recent crowdfunding effort, plans are now in motion to monitor the entire night sky for laser pulses. But while these bright flashes would be relatively easy to find, advanced life might be using something far more elusive: neutrinos. Tiny subatomic particles that are streaming through you by the trillions every second. These ghost particles can pass through entire planets and not touch a single atom. It takes a giant room like this to detect just a handful of them per day. But researchers recently proved neutrino communication is possible by sending a simple message through 240 meters of rock. If advanced life is using them to communicate, their signals could travel anywhere, through any obstacle, at the speed of light. Their messages could be streaming through us right now, and we would have no idea. Or maybe intelligent life is taking an entirely different approach to communication, using space-time itself as a medium. By manipulating high-gravity objects, they could in theory create pattern distortions of space-time, which could ripple through the universe in all directions. But making gravity waves strong enough to be detectable would be extremely energy intensive. Maybe they're up to something far simpler. Placing giant sunshades into orbit around a star could block out starlight in distinct patterns, like a kind of cosmic Morse code. And even though it might take years to blink out a basic message, a system like this would require little effort to sustain. But the most sci-fi possibility of all is that they have left messages in our DNA. Some have proposed that certain sequences of our genes could contain hidden messages. Easter eggs in our genetic code, placed by a life-designing higher intelligence. But far-flung scenarios like this are overshadowed by a more sobering possibility. Maybe we're just in the wrong place, at the wrong time.
लो भाई, ग्रोसरी के बहाने आज मॉर्निंग वॉक भी हो गई।
गुड। अच्छी सेहत सबसे इम्पोर्टेंट है अम्मी।
सिर्फ मेरी ही नहीं, मेरे पोते की सेहत भी।
नेस्ले सेरेलैक पेट भर के तो खिलाती हूँ।
एक बढ़ते बच्चे को इतनी ग़िज़ाइयत की ज़रूरत होती है। इन सब की ग़िज़ाइयत एक साथ खिला सकती हो?
इसके मुट्ठी जितने पेट में ये कैसे आएगा अम्मी?
ऐसे, क्योंकि सेरेलैक में गंदम, चावल और फलों के साथ शामिल है आयरन, विटामिन्स और प्रोबायोटिक्स, जिससे बढ़ते बच्चों को मिले ठोस और सही ग़िज़ाइयत।
अब समझ आया कि बेबी को रोज सेरेलैक भी खिलाना कितना जरूरी है।
समझदार माँ
और दादी का इंतखाब
नेस्ले सेरेलैक, हर प्याले में ग़िज़ाइयत का एतमाद।
फ्रॉम नेस्ले।
Using a detailed computer model of our galaxy, researchers have estimated that intelligent life was possibly most concentrated 4 billion years ago, and closer to the center of the galaxy. If true, then we would exist on the outskirts, light years away and billions of years too late to a galactic golden age. Maybe they were here, millions of years ago.
Witness to a whole different planet. By now, they might all be long gone, and we could be living in a galactic graveyard. It may not be their signals that we find one day, but their relics. As it turns out, our chances of finding an alien civilization depend heavily on their average survival time. If the average lifetime is something like 100 years, then they will blip in and out of existence, rarely overlapping, and our chances of finding one alive are slim. But if they survive for thousands of years or more, then our chances will skyrocket as the potential for overlap expands. But what if they're not communicating at all? There's still a way we could find them. We tend to assume that alien intelligence would share our motivation to communicate. But they may find the prospect of making contact too dangerous or too futile. If this is the case, then we have to get more creative in our search. In 2015, astronomers watched as this normal-seeming star began to dim in erratic ways, unlike anything they'd seen before. The cause is probably a giant dust cloud or a shattered moon blocking the light. But it has all the hallmarks of something else. An alien megastructure. And even though this explanation looks unlikely, it hints at a new way of finding intelligent life. Not listening for signals, but looking for their technology directly. Not searching for messengers, but searching for engineers. And to do that, we have to wonder, what mind-boggling alien technology should we be looking for? Each alien civilization would be wildly different, but classifying them by their energy usage will give us insights into what technology they might be using. The Kardashev scale divides them into 3 levels. Type 1 would have a mastery of their home planet, using all the energy available on it. Type 2 would have mastery over their star, harnessing all its solar energy. Type 3 would have mastery over their entire galaxy and would be more foreign to us than we are to amoeba. But before we go searching for alien super technology, how would we find civilizations like our own that have yet to reach Type 1? When a typical planet passes in front of its star, we see the starlight dim sharply. But observing a more gradual fall-off of starlight could be evidence of a dense ring of satellites, a Clark belt. Spotting this type of light curve wouldn't be a smoking gun, but rings around rocky planets are unusual, and it could point us in the right direction. Just as alien vegetation would leave a biosignature in its atmosphere, alien technology would leave a technosignature. Silicon produces a recognizable light curve similar to chlorophyll. Spotting this signal could point us to the presence of alien solar cells. And something more nefarious might also leave its mark on a foreign atmosphere. Alien pollution. Certain pollutants like chlorofluorocarbons aren't produced by nature and could be detectable even in small amounts. These chemicals could even linger long after a civilization dies, pointing us to the remains of an extinct alien race. Such a discovery could give us crucial guidance on how to avoid our own extinction. And there's another universal hazard we would be familiar with.
अब कोका कोला की 2 लीटर बोतल सिर्फ 220 रुपए में। खाना बनाए मैजिकल कोका कोला के साथ।
Any civilization that uses huge amounts of energy will produce huge amounts of waste heat. This excess heat could prove a serious threat, just as climate change does to us. But it could also leave a telltale signal. Finding waste heat radiating from alien planets or other regions of space could point the way to intelligent activity. If not exterminated by their own technology, some life forms may achieve total control over their planet and become a Type 1 civilization. this mastery would come incredible powers. Control over all their world's ecosystems, its resources, and even its weather. But no matter how advanced, every planetary civilization will face the same cosmic threats we do. Gamma ray bursts, supernovas, and asteroid impacts will be a risk factor for any terrestrial race. Some might decide to flee to intergalactic space, reducing their exposure to existential risks, making their home in the voids between the stars. If so, then our search will have to encompass the entire swath of the universe. But alien life that decides to stay planet-bound will need long-term protection. The best way to protect your world will be the ultimate in home defense. A planetary shield. These shields would cause a telltale dimming pattern during transit, and could also emit a detectable heat signature. Large-scale astroengineering like this would require a colossal amount of resources. And the easiest way to get them may not be from mining planets, but from mining asteroids. They are resource-rich and easier to manipulate because of their lower gravity. Searching distant asteroid fields for temperature or chemical anomalies could indicate alien mining activity. Eventually, though, asteroids might not be enough. Since our civilization is so new, any other intelligent life is likely to be more advanced than us. So we should think twice before revealing our presence. But alien super civilizations won't just be looking for resources. They will also need staggering amounts of energy. Stars output billions of times more energy than planets receive. To harness it all requires building something truly mind-boggling. Dyson spheres are enormous megastructures that encircle a star, designed to capture its entire energy output. They could also double as vast habitats for life. A solid shell would be physically unstable, so instead of a sphere, we might find a cloud of objects, a Dyson swarm. matter their design, they would generate an enormous amount of infrared waste heat. And they could also eclipse or even block out the star's light entirely. Dyson spheres could also be built around black holes, which could have a smaller radius and collect thousands of times more energy. Any beings that come to harness their star's entire energy output will reach the next level on the Kardashev scale. A Type 2 civilization. This level of mastery would imply an astounding capability. Star lifting is the practice of harvesting stellar material and could provide thousands of planets' worth of resources. This process would also allow you to lower the temperature of a star, postponing its death by billions of years. In about 1 billion years' time, our own sun will grow too hot for life on Earth. If we ever find evidence of star lifting, it could inspire us to one day do the same and prolong the game of life. Eventually, there may be life that outgrows its star and needs even more energy. To branch out across the galaxy, life forms this advanced will probably need near-light speed travel. And if they do have this capability, there's a chance we could catch them in the act. Alien starships that hit the brakes at light speed could leave behind a long trail of ionized gas. These trails might emit detectable infrared radiation. Strokes of light painted by masters of the universe. Once life forms have harnessed all the energy their galaxy can provide, they will achieve unimaginable power. A Type 3 civilization. This cosmic virtuosity would be totally unfathomable to us. Life that has built billions of Dyson spheres and can create stars at will. In theory, their thirst for energy could make a whole galaxy go dark. So one way to search for Type 3 life forms is to look for what's not there. In distant space, there are huge voids between clusters of galaxies where no light emanates. These voids were once thought to be evidence of advanced life having harnessed the energy from every star in the region. But it turns out they are naturally occurring features of the universe. and a recent analysis of nearby galaxies revealed no evidence of any galactic-scale civilizations. In theory, cosmic architects could assemble enormous planetary systems far more intricate than anything nature could produce. One possible system that would be gravitationally stable involves 9 sun-like stars orbiting a supermassive black hole, which could support 550 Earth-like planets in a habitable zone. These artisanal solar systems could make ideal long-term habitats, or could even function as an alien nature reserve, with each planet hosting a different strain of life. It's hard to imagine any life forms more advanced than this. But in theory, there could be beings that control or created our universe itself.
New Nescafe Sachet, अब सिर्फ 25 रुपए में।
नेस्कैफे, बनाओ अपनी दुनिया।
तो अपनी फास्ट पेस्ड लाइफ को एक हीरो की तरह मैनेज करने के लिए ले आए लिव इट एंड लिव एक्स्ट्राऑर्डिनरी।
Researchers are beginning to test the idea that reality itself is just a simulation or an experiment run by some higher order being. Anything this advanced would transcend our ideas of life itself, as they would exist outside of time and space. In a way, the search for intelligent life is an evolution of the age-old search for God. Both are driven by a longing for truth and connection with something bigger than ourselves. And what if we do find a signal one day? What happens when the ancient dream becomes a reality? Just knowing they're out there would profoundly change how we see ourselves. For the first time, we would feel a true sense of cosmic brotherhood. Studying their messages or technology could lead us to huge advancements and help secure our own long-term survival. the possibility of meaningful two-way communication would be bleak. Separated by hundreds or thousands of light years, we would be studying these civilizations as they were in the deep past. And our experience of language could be entirely foreign to them. But what if, after all our searching, we never find another sign of intelligence? What if we really are alone? We can never be truly sure, as there will always be distant galaxies too far to ever study. But never finding any evidence would mean that our place in the universe is truly unique. It would saddle us with an immense responsibility to keep the flame of intelligence alive. Just as ancient civilizations speak to us through their monuments, we could build monuments of our own for future life to discover. Cosmic time capsules preserving a record of our achievements and our knowledge. Perhaps other races will do the same, and these memory vaults could become connected over time, each new civilization adding a link. It could be our destiny to be the first link in this chain, to be the founders of a galactic encyclopedia built upon by future life forms we will never meet.
in all of time, on all the planets of all the galaxies in space, what civilizations have risen, looked into the night, seen what we see, asked the questions that we ask.
Life seems to have conquered every corner of the earth. How did all this complexity emerge?
Living organisms are created by chemistry. We are huge packages of chemicals. Now, what are the ideal conditions for chemistry? Well, first, you need energy. But not too much. What you want is just the right amount, and planets, it turns out, are just right because they're close to stars, but not too close. You also need a great diversity of chemical elements. And you need liquids, such as water. Why? Well, in gases, atoms move past each other so fast that they can't hitch up. In solids, atoms stuck together. They can't move. In liquids, they can cruise and cuddle and link up to form molecules.
Liquid water is just so good for getting evolution going. Molecules can dissolve in the water, form more complex chains.
Now, where do you find such Goldilocks conditions? Well, planets are great. And our early Earth was almost perfect. It was just the right distance from its star to contain huge oceans of liquid water. And deep beneath those oceans, at cracks in the Earth's crust, fantastic chemistry began to happen, and atoms combined in all sorts of exotic combinations.
tribes have adapted to survive the most hostile conditions. Arid deserts, the frozen Himalayas, in trenches under thousands of tons of pressure in the ocean deeps.
New research suggests that life emerged over 4 billion years ago, when Earth was an alien and deadly planet. At the time, Earth was ravaged by intense volcanism and an asteroid storm that lasted 100 million years. But even in these extreme conditions, life quickly found a foothold.
As soon as the Earth cooled off after its formation, we know that life began here.
Because it happened quickly here on Earth, we think it's going to happen quickly on other planets as well.
We know that the galaxy is awash in water. It's awash in organic molecules and complex chemistry. All of the things that we know were necessary for life to begin on this planet exist in abundance throughout the galaxy. Did something similar to what happened on our own planet happen on those other planets?
Among this abundance of worlds, many will be deadly to life as we know it. There will be planets in the habitable zone that are scorched, frozen, and suffocated by poison gases. Many will lack an atmosphere critical for temperature regulation, or have one that is deadly. Venus, once thought to potentially support life, is now sterilized by a crushing toxic atmosphere. But life may not be confined to the habitable zone. Far from the warmth of their star, the moons of giant gas planets may be hidden oases for life. Their energy comes not from starlight, but from gravity, the lurching push and pull of the host planet. Icy Enceladus has it all. A huge subsurface ocean with hydrothermal vents spewing the chemistry of life. Titan is especially alluring. Larger than Mercury and speckled with methane lakes and organic compounds. In 2026, NASA plans to send a drone to Titan, seeking out signs of life in its valleys and craters.
For years, we've looked to Mars as our best bet for finding life in the solar system. The idea that Venus could have been habitable in the past is also quite plausible. Venus could have maintained liquid water for around 3 billion years, only becoming uninhabitable just 750 million years ago. Life could have been present on the surface and evolved the ability to float up into the clouds. Up here, the pressures drop and the temperatures become balmy, comparable to that of the Earth. The idea of life on Venus isn't that crazy.
The discovery of just one bacteria on Mars, or any other body of the solar system, would indicate that the whole chain of evolutions, cosmic, chemical, and biological, is at work everywhere. elsewhere in the universe would be more the rule than the exception.
Within all of our lifetime, we're going to understand that there is life on other bodies in the solar system. We're going to understand the implications of that for evolution of life here on Earth. We're going to find planets around other stars that we can say we see potential signs of habitability in their atmospheres. That's all going to happen in the next 10 to 20 years. How exciting is that? We're on the verge of things that people have wondered about for millennia. Are we alone? And here we are on the verge of finding that out.
Our universe is close to 14 billion years old, and there are planets out there that are 3 times as old as Earth. With all that time to develop, there could be life out there far more advanced than us.
The Big Bang created only the 3 lightest elements: hydrogen, helium, and lithium. The heavier elements that make life possible were only created later in the ultra-dense cores of stars. And for those elements to wind up inside your body, those stars would have to explode.
Red dwarf stars can live up to 10 trillion years, bathing their planets in starlight for eons. Life is much more probable on these timescales, where conditions are stable for vast periods of time. Any beings living close to these stars would have to contend with violent solar flares that continually threaten extinction. Many of these planets would be tidally locked. One side permanently exposed to the sun, the other frozen in darkness. have any hope of finding alien life, we have to know what to look for. But where do we begin? How do we narrow down a seemingly infinite set of possibilities? There's one thing we know for sure. Nature will have to play by her own rules. No matter how strange alien life might be, it's going to be limited by the same physical and chemical laws that we are. On top of this, each alien environment will further limit what kinds of life forms can evolve there. Despite these natural boundaries, the possibilities are staggering to imagine. Trillions of planets, each a unique cauldron of chemicals undergoing their own complex evolution. To guide our thinking, this museum of alien life will be divided into two exhibits. Life as we know it, home to beings with biochemistries like ours, and life as we don't know it, home to beings that challenge our concept of life itself. Before we venture too far into the unknown, we have to ask ourselves, what if alien life is more like us than we think? If there's one feature that unites us with the other specimens in this museum, it's carbon.
Carbon is ubiquitous. It's one of the most common elements in the universe, and it's very good at forming large, stable molecules.
Carbon has the rare ability to form four-way bonds with other elements, and to bind to itself in long, stable chains, enabling the formation of huge, complex molecules. This versatility makes carbon the centerpiece in the molecular machinery of life. And the same carbon compounds that we use have been found far from Earth, clinging to meteorites, and floating in far-off clouds of cosmic dust. The building blocks of life, drifting like snow through the universe. And if alien life has selected other carbon compounds for their biochemistry, they will have plenty to choose from. Scientists recently identified over 1 million possible alternatives to DNA, all carbon-based. If we ever discover other carbon-based life forms, we would be fundamentally related. They would be our cosmic brethren. But would they look anything like us? If they hail from Earth-like planets, we could share even more in common than just our biochemistry.
What would life be like on other planets if it is evolved? Would it be like the world today here on Earth? Or would it be completely different? There are those who argue that from the argument of convergent evolution, if conditions on other planets are similar to here, then we would see very similar life forms. Animal and plant-like organisms that look very familiar.
On Earth, certain features like eyesight, echolocation, and flight have evolved multiple times independently in different species. This process of convergent evolution could extend to alien planets like Earth, where creatures face similar environmental pressures. It's no guarantee, but there could be certain universalities of life. The greatest hits of evolution on repeat across the universe. Each feature would be attuned to its local environment. Dimly lit planets would produce huge eyes to suck in extra light, like nocturnal mammals.
Some people have gone so far as to say that human-type organisms, humanoids, will occur on other planets.
The existence of other human-like organisms seems unlikely, given the long, convoluted chain of events that produced us. But we can't rule it out. If just one in every 100 trillion Earth-like planets produced a human-like form, there could still be thousands of creatures like us out there. Convergent evolution is also rampant in plant life, and C4 photosynthesis has arisen independently over 40 times. Would alien plants look like ours, or something else entirely? On Earth, plants appear green because they absorb the other wavelengths in the sun's light spectrum. But stars come in many colors. And alien plants would evolve different pigments to adapt to their sun's unique spectrum. Plants feeding off hotter stars could appear redder by absorbing their energy-rich bluer light. Around dim red dwarf stars, vegetation could appear black, adapted to absorb all visible wavelengths of light. Earth itself may have once appeared purple due to a pigment called retinol that was an early precursor to chlorophyll. Some think that retinol's molecular simplicity could make it a more universal pigment. If so, we may find that purple is life's favorite color. But the color of alien vegetation is more than just a curiosity. It's chemical information that could be seen from light years away. Earth plants leave a signature bump in the light reflected off our planet. Finding a similar signal from another world could point the way to alien vegetation. Perhaps this will be our first glimpse at alien life, a vibrant hue cast by a distant world.
happens when you change the day length of a planet? What happens when you change the tilt of a planet? What happens when you change the shape of the orbit? What happens when you change the gravity of a planet?
Planets with long elliptical orbits would see drastic seasons. There could be worlds that appear dead for thousands of years, then suddenly spring to life. Most of the rocky planets discovered so far have been massive super-Earths. How would life evolve on these worlds? In the seas, gravity may not matter much at all.
A high-gravity planet isn't high gravity all over. If you're in the sea, and that's where all life starts, there's very nearly no gravity because you're much the same density as the stuff around you. It's when the animals come out on land that they feel the gravity.
High G-forces would necessitate large bones and muscle mass in complex life on land. They would also demand a more robust circulatory system. And plant life could be stunted by the energy cost of carrying nutrients under stronger gravity. Low-gravity planets would more easily lose their atmospheres to space and lack a magnetic field to protect from cosmic rays. But smaller worlds could be home to secret oases. Huge cave systems that provide hideouts for life. The smallest possible habitable planets are estimated at 2.5% Earth's mass. If surface life does evolve on these worlds, it could be a sight to behold. Plant life could grow to towering heights, able to carry nutrients higher in lesser gravity. Without the need for bulky skeletons and muscle mass, animals could have body types that boggle the mind. Here on Earth, it took 3 billion years for evolution to produce complex plant and animal life. Simpler organisms are hardier, more adaptable, and more widespread. The largest collection in the Museum of Alien Life would likely be the Hall of Microbes. Yet finding even the tiniest alien microbe would be a profound discovery. bite-sized life could leave a big footprint. Like stromatolites on Earth, layers of microbes could build up into huge rock mounds over time, leaving behind eerie structures. And in big enough numbers, some alien bacteria could leave a distinct biosignature by exhaling gases that wouldn't coexist naturally, like oxygen and methane.
There's ways to make oxygen without life, there's ways to make methane without life.
Like exoplanet in the habitable zone is probably only 20 light years away and can be seen with the naked eye.
Most brown dwarfs are too hot to support life as we know it, but some are just cold enough. All the prime elements for life have been detected inside their atmospheres. And within these clouds, some layers would provide ideal temperatures and pressures for habitability. There could be photosynthetic plankton in these skies, kept aloft by churning upwinds. And with enough force, these upwinds could even support larger, more complex life. Predators. This raises a crucial question. What if we've been looking in all the wrong places? What if nature has other ideas? Most of the universe is too cold or too hot for liquid water and the biochemistry that supports life as we know it. But in case our biases are misleading, we have to cast a wide net to search for life outside the habitable zone, in places that seem wildly hostile to us. Exotic environments will demand exotic biochemistries, and while no element can match carbon's versatility, one contender is a frontrunner. At first glance, silicon seems similar to carbon. It forms the same four-way bonds and is also abundant in the universe. But a closer look reveals that these two elements are false twins. Silicon bonds are weaker and less prone to forming large, complex molecules. Despite this, they can withstand a wider range of temperatures, opening up intriguing possibilities.
Life based on the silicon atom instead of carbon would be more resistant to the extreme cold.
providing a whole new range of weird forms.
But silicon has a problem. In the presence of oxygen, it binds into solid rock. To avoid turning to stone, silicon beings might be confined to oxygen-free environments, like Saturn's frigid moon, Titan. Its vast lakes of liquid methane and ethane could be an ideal medium for silicon-based life, or other radical biochemistries. Without ample sunlight, beings on worlds like Titan would likely be chemosynthetic, deriving their energy by breaking down rocks. Such life forms could have ultra-slow metabolisms and life cycles measured in millions of years. In high temperatures, typically rigid silicon-oxygen bonds become more flexible and reactive, triggering more dynamic chemistry. This has led to a truly bizarre proposal: silicon-based life forms that live inside molten silicate rock. In theory, these forms could even exist deep beneath the Earth inside magma chambers as part of a shadow biosphere. If so, then the aliens are right under our noses. Other shadow biospheres have been proposed, forms of life living alongside us that we don't even know are here, including tiny RNA-based life small enough to go undetected by existing instruments. Clouds of dust in empty space might seem like the last place you'd expect to find anything living. But when cosmic dust makes contact with plasma, a type of ionized gas, something strange happens. In simulated conditions, dust particles have been seen spontaneously self-organizing into helical structures that resemble DNA. These plasma crystals even begin to exhibit lifelike behavior, replicating, evolving into more stable forms, and passing on information. Plasma is the most common state of matter in the universe. If complex evolving plasma crystals really exist, and if they can be considered life, they could be its most common form. When massive suns explode, some collapse into ultra-dense cores called neutron stars. Hulking masses of atomic nuclei crammed together like sardines. Conditions on the surface are mind-boggling. Gravity is 100 billion times stronger than Earth's. But beneath their iron nuclei crust lies something strange. A hot, dense sea of neutrons and subatomic particles. Stripped of their electron shells, these nuclei would obey entirely different laws of chemistry, based not on the electromagnetic force, but the strong nuclear force which binds nuclei together. In theory, these particles could link up to form larger macronuclei, which could then combine into even bigger supernuclei. If so, then this bewildering environment would mimic the basic conditions for life: heavy nucleon molecules floating in a complex particle ocean. Some scientists have proposed the unimaginable. Exotic life forms drifting through the strange particle sea, living, evolving, and dying on incomprehensibly fast timescales. Life is not something that has to evolve naturally. It can be designed. And once intelligence is introduced into the evolutionary process, a Pandora's box is opened. Freed from typical biological limitations, synthetic and machine-based life could be the most successful of all. It could thrive almost anywhere, including the vacuum of space, opening up vast frontiers unavailable to biological organisms. And compared to the glacial pace of natural selection, technological evolution allows exponentially faster growth, adaptability, and resilience. By some estimates, autonomous self-replicating machines could colonize an entire galaxy in as little as 1 million years. We can't predict how hyper-intelligent life would organize itself. But in theory, there could be convergent evolution at play. The electrical properties of silicon might make it a universal basis for machine intelligence, a redemption for its biological shortcomings. the universe ages, perhaps machine intelligence will come to dominate, and naturally occurring biological life will be viewed as a quaint starting point. Perhaps we ourselves will lead this transition, and the great human experiment will be merely a first link in a sprawling intergalactic chain of life.
Has said that one does not meet oneself until one catches the reflection from an eye other than human. One day that eye may be that of an intelligent alien. And the sooner we eschew our narrow view of evolution, the sooner we can truly explore our ultimate origins and destinations.
The most complex object known in the universe is the human brain. These 86 billion neurons have given us the power to transform our planet. But is this the best nature can do? We now know there are something like 10 billion trillion habitable planets in the universe. 10 billion trillion chances for the brain to be eclipsed by something else. The search for intelligent life is more than just a scientific curiosity. It's driven by a deep desire to connect with something greater. Finding an alien civilization wouldn't just reveal we're not alone. It could chart a new course of evolution for our species. And unlike primitive life, alien intelligence could be detectable thousands of light years away, making them potentially easier to find. What do they know that we don't? And how do we make contact? We're not the first to wonder. Years ago, we dreamed of lighting huge rings of fire in the Sahara Desert to signal our presence. And in the 1860s, a French poet proposed a patchwork of giant mirrors, reflecting sunlight to Mars in the form of the Big Dipper. But if you want to send a signal across an ocean of space, bonfires and reflected sunlight won't help you much. Even a nuclear war on a nearby planet would be virtually impossible to detect with current technology. To really get your message across, you need a form of light you can't even see. Radio waves are ideal for carrying information long distance, because compared to other forms of light, they travel more freely through interstellar gas and dust. That's why SETI, the search for extraterrestrial intelligence, has focused almost entirely on scanning for radio signals, whether intentional messages or byproducts of technology. Our own radio transmissions have now traveled 100 light years and reached 75 star systems, some of which include potentially habitable planets. And if alien intelligence lies beyond this bubble of signals, they could still infer life on Earth by spotting oxygen in our atmosphere. Thanks to the SETI Institute and the recent Breakthrough Listen project, we have now scanned tens of millions of stars for signals. But despite all this, after 6 decades of searching, nothing. Only a series of false alarms and dead-end leads. We call it the Great Silence. But in reality, the search has barely even begun. There are 2 trillion other galaxies out there that are still too far away for practical study. If space were the size of all Earth's oceans, we would have searched less than a pool's worth of water for signs of intelligent life. On top of this, we might even be looking for the wrong thing. There's more than one way to communicate across space. And alien life might view radio as primitive technology. We have to consider every possible alternative, from the practical to the unimaginable. The search is now underway for a different type of signal, one we could even spot with the naked eye: laser light. High-powered laser bursts can outshine a star by thousands of times and can carry far more data per second than radio. We would have to be in direct line of sight to detect the beam. But spread across many light years, they would widen to encompass entire planets and moons. Fleets of laser beacons could be used to sweep the entire galaxy, like alien lighthouses in a cosmic sea. Thanks to a recent crowdfunding effort, plans are now in motion to monitor the entire night sky for laser pulses. But while these bright flashes would be relatively easy to find, advanced life might be using something far more elusive: neutrinos. Tiny subatomic particles that are streaming through you by the trillions every second. These ghost particles can pass through entire planets and not touch a single atom. It takes a giant room like this to detect just a handful of them per day. But researchers recently proved neutrino communication is possible by sending a simple message through 240 meters of rock. If advanced life is using them to communicate, their signals could travel anywhere, through any obstacle, at the speed of light. Their messages could be streaming through us right now, and we would have no idea. Or maybe intelligent life is taking an entirely different approach to communication, using space-time itself as a medium. By manipulating high-gravity objects, they could in theory create pattern distortions of space-time, which could ripple through the universe in all directions. But making gravity waves strong enough to be detectable would be extremely energy-intensive. Maybe they're up to something far simpler. Placing giant sunshades into orbit around a star could block out starlight in distinct patterns, like a kind of cosmic Morse code. And even though it might take years to blink out a basic message, a system like this would require little effort to sustain. But the most sci-fi possibility of all is that they have left messages in our DNA. Some have proposed that certain sequences of our genes could contain hidden messages, Easter eggs in our genetic code, placed by a life-designing higher intelligence. But far-flung scenarios like this are overshadowed by a more sobering possibility. Maybe we're just in the wrong place, at the wrong time. Using a detailed computer model of our galaxy, researchers have estimated that intelligent life was possibly most concentrated 4 billion years ago, and closer to the center of the galaxy. If true, then we would exist on the outskirts, light years away and billions of years too late to a galactic golden age. Maybe they were here millions of years ago, witness to a whole different planet. By now, they might all be long gone, and we could be living in a galactic graveyard. It may not be their signals that we find one day, but their relics. As it turns out, our chances of finding an alien civilization depend heavily on their average survival time. If the average lifetime is something like 100 years, then they will blip in and out of existence, rarely overlapping, and our chances of finding one alive are slim. But if they survive for thousands of years or more, then our chances will skyrocket as the potential for overlap expands. But what if they're not communicating at all? There's still a way we could find them. We tend to assume that alien intelligence would share our motivation to communicate. But they may find the prospect of making contact too dangerous or too futile. If this is the case, then we have to get more creative in our search. In 2015, astronomers watched as this normal-seeming star began to dim in erratic ways, unlike anything they'd seen before. The cause is probably a giant dust cloud or a shattered moon blocking the light, but it has all the hallmarks of something else. An alien megastructure. And even though this explanation looks unlikely, it hints at a new way of finding intelligent life. Not listening for signals, but looking for their technology directly. Not searching for messengers, but searching for engineers. And to do that, we have to wonder, what mind-boggling alien technology should we be looking for? Each alien civilization would be wildly different, but classifying them by their energy usage will give us insights into what technology they might be using. The Kardashev scale divides them into 3 levels. Type 1 would have a mastery of their home planet, using all the energy available on it. Type 2 would have mastery over their star, harnessing all its solar energy. Type 3 would have mastery over their entire galaxy and would be more foreign to us than we are to amoeba. But before we go searching for alien super technology, how would we find civilizations like our own that have yet to reach Type 1? When a typical planet passes in front of its star, we see the starlight dim sharply. But observing a more gradual fall-off of starlight could be evidence of a dense ring of satellites, a Clark belt. Spotting this type of light curve wouldn't be a smoking gun, but rings around rocky planets are unusual, and it could point us in the right direction. Just as alien vegetation would leave a biosignature in its atmosphere, alien technology would leave a technosignature. Silicon produces a recognizable light curve similar to chlorophyll. Spotting this signal could point us to the presence of alien solar cells. And something more nefarious might also leave its mark on a foreign atmosphere. Alien pollution. Certain pollutants like chlorofluorocarbons aren't produced by nature and could be detectable even in small amounts. These chemicals could even linger long after a civilization dies, pointing us to the remains of an extinct alien race. Such a discovery could give us crucial guidance on how to avoid our own extinction. And there's another universal hazard we would be familiar with. Any civilization that uses huge amounts of energy will produce huge amounts of waste heat. This excess heat could prove a serious threat, just as climate change does to us. But it could also leave a telltale signal. Finding waste heat radiating from alien planets or other regions of space could point the way to intelligent activity. If not exterminated by their own technology, some life forms may achieve total control over their planet and become a Type 1 civilization. With this mastery would come incredible powers. Control over all their worlds. Some might decide to flee to intergalactic space, reducing their exposure to existential risks, making their home in the voids between the stars. If so, then our search will have to encompass the entire swath of the universe. But alien life that decides to stay planet-bound will need long-term protection. best way to protect your world will be the ultimate in home defense. A planetary shield. These shields would cause a telltale dimming pattern during transit, and could also emit a detectable heat signature. Large-scale astroengineering like this would require a colossal amount of resources. And the easiest way to get them may not be from mining planets, but from mining asteroids. They are resource-rich and easier to manipulate because of their lower gravity. Searching distant asteroid fields for temperature or chemical anomalies could indicate alien mining activity. Eventually, though, asteroids might not be enough. Since our civilization is so new, any other intelligent life is likely to be more advanced than us. So we should think twice before revealing our presence. But alien super civilizations won't just be looking for resources. They will also need staggering amounts of energy. Stars output billions of times more energy than planets receive. To harness it all requires building something truly mind-boggling for life. A solid shell would be physically unstable, so instead of a sphere, we might find a cloud of objects, a Dyson swarm. No matter their design, they would generate an enormous amount of infrared waste heat. And they could also eclipse or even block out the star's light entirely. Dyson spheres could also be built around black holes, which could have a smaller radius and collect thousands of times more energy. Any beings that come to harness their star's entire energy output will reach the next level on the Kardashev scale. A Type 2 civilization. This level of mastery would imply an astounding capability. Star lifting is the practice of harvesting stellar material and could provide thousands of planets' worth of resources. This process would also allow you to lower the temperature of a star, postponing its death by billions of years. In about 1 billion years' time, our own sun will grow too hot for life on Earth. If we ever find evidence of star lifting, it could inspire us to one day do the same. And prolong the game of life. Eventually, there may be life that outgrows its star and needs even more energy. To branch out across the galaxy, life forms this advanced will probably need near-light speed travel. And if they do have this capability, there's a chance we could catch them in the act. Alien starships that hit the brakes at light speed could leave behind a long trail of ionized gas. These trails might emit detectable infrared radiation. Strokes of light, painted by masters of the universe. Once life forms have harnessed all the energy their galaxy can provide, they will achieve unimaginable power. A Type 3 civilization. So one way to search for Type 3 life forms is to look for what's not there. In distant space, there are huge voids between clusters of galaxies where no light emanates. These voids were once thought to be evidence of advanced life having harnessed the energy from every star in the region. But it turns out they are naturally occurring features of the universe. And a recent analysis of nearby galaxies revealed no evidence of any galactic-scale civilizations. In theory, cosmic architects could assemble enormous planetary systems far more intricate than anything nature could produce. One possible system that would be gravitationally stable involves 9 sun-like stars orbiting a supermassive black hole, which could support 550 Earth-like planets in a habitable zone. These artisanal solar systems could make ideal long-term habitats, or could even function as an alien nature reserve, with each planet hosting a different strain of life. It's hard to imagine any life forms more advanced than this. But in theory, there could be beings that control or created our universe itself. Researchers are beginning to test the idea that reality itself is just a simulation, or an experiment run by some higher order being. Anything this advanced would transcend our ideas of life itself, as they would exist outside of time and space. In a way, the search for intelligent life is an evolution of the age-old search for God. Both are driven by a longing for truth and connection with something bigger than ourselves. And what if we do find a signal one day? What happens when the ancient dream becomes a reality? Just knowing they're out there would profoundly change how we see ourselves. For the first time, we would feel a true sense of cosmic brotherhood. Studying their messages or technology could lead us to huge advancements and help secure our own long-term survival. But the possibility of meaningful two-way communication would be bleak. Separated by hundreds or thousands of light years, we would be studying these civilizations as they were in the deep past. And our experience of language could be entirely foreign to them. But what if, after all our searching, we never find another sign of intelligence? What if we really are alone? We can never be truly sure, as there will always be distant galaxies too far to ever study. But never finding any evidence would mean that our place in the universe is truly unique. It would saddle us with an immense responsibility to keep the flame of intelligence alive. Just as ancient civilizations speak to us through their monuments, we could build monuments of our own for future life to discover. Cosmic time capsules preserving a record of our achievements and our knowledge. Perhaps other races will do the same, and these memory vaults could become connected over time, each new civilization adding a link. It could be our destiny to be the first link in this chain, to be the founders of a galactic encyclopedia, built upon by future life forms we will never meet.
We all know how it goes. One day we're born, one day we die. Everything that happens in between we know and understand, but everything that happened before and will happen after, we know nothing about. As a result, it's really difficult to say what exactly the meaning or importance for us being here is. If we can't tell how we came or where we came from, how can we know why we're here? In the same vein, if we don't know where we're going or what we're going to become, how can we tell if any of our present actions have any significance at all? It is this uncertainty of both our collective pasts and futures that has allowed the question, what is the meaning of life, to plague humanity ever since we became sentient. We've never been able to objectively answer this question as a species. However, a lot of us have found comfort in many different ideologies to at least subdue the anxiety that it causes. In many different religions, a deity made the entire universe, put us all in it, and whatever we do on this earth will be used to determine when and how we spend eternity afterwards. For some others, the meaning of life is the love we share with friends, family, and our loved ones. Some others believe the existence of life in itself is what makes it worth living. But for nihilists, life is meaningless. All action, suffering, emotions, both good and bad, are entirely senseless and meaningless. This is nihilism, the belief in nothing. At some point in our lives, many of us have been faced with nihilistic thoughts. We're hit by a strong sense of purposelessness, like our lives have no meaning, and we have no intrinsic value. Usually, this happens when we begin to question our old beliefs, but also just before we get new ones to hold on to. It's in that phase where you're growing out of your parents' beliefs, learning new things, getting new experiences, and forming your own views about the world. And usually, all of these thoughts begin with one simple question. Why? A 3-lettered monosyllabic word that's capable of making anything and everything that feels like the rock of your foundation start to become slippery. Like quicksand dragging you into the misery that maybe, just maybe, your whole life hasn't been what you thought it was. Just pause and take a moment to think about your core values and just ask the question, why? Why do you believe those things? Where did they come from? Who did they come from? Keep asking and eventually you'll arrive at a point where there's no longer an answer. You'll arrive at nothing. All the religions of the world, all of our scientific discovery, but yet the question why is one that we still cannot answer. And so for the nihilist, it is at this point that they come to the conclusion that there is no why. There is no answer. There's simply nothing. As Alan Watts once wrote, life is nothing more than a trip from the maternity ward to the crematorium. It's really in the name. The term nihilism comes from the Latin word nihil, which translates to nothing, and ism, which translates to ideology. It's the ideology of nothing. But that doesn't really help us in understanding it completely. Usually, people confuse nihilism for pessimism, but they are very different from each other. Pessimists believe in the worst outcome. They have a downtrending view of the world, and tend to focus on the negatives in life, because they believe that, in the end, evil will always overcome good, and this is what makes them different. Pessimists believe that there's good in the world, but they just don't think humans are capable of doing it, at least in its entirety. Nihilists, on the other hand, do not believe in anything. They don't believe that there's evil in the world, neither do they believe that there's good in the world. In the mind of the nihilist, the world simply exists and humans created morality, thereby creating good and evil. Let's take the glass cup metaphor for instance. Optimists say you should see the glass as half full, while pessimists say we should see the glass as half empty. Nihilists, they say throw the entire cup away, because what does it matter if it's full or empty? Full, empty, good, bad, it's all irrelevant. We're all going to die.
Well, howdy from Texas A&M, and welcome and appreciate the opportunity to be here with this webinar. Looks like an outstanding event. Before I start, I'll give you a few disclosures. I've been doing research on creatine for over 30 years, and some of that has involved industry-funded projects. We currently are doing a study on elderly and cognition funded by the Wood Next Foundation, and I serve as chair of the Creatine for Health Scientific Advisory Board, which is trying to raise awareness about the health aspects of creatine, which we'll talk a lot about today. So without further ado, let me get into, and before we start, if you know anything about the landscape of sport nutrition is evolving into active nutrition and nutrition for maintaining health and performance and cognition as you age. And if you look at the history here, creatine's really leading this charge as a nutrient that was once thought to be for sports and performance and training, now has evolved into a health substance. And you can see this is now creatine's in all type of products. If you look at the market, it's expanded to active nutrition, general health, aging in particular, and then nutrition for disease management under certain clinical conditions where creatine has been involved. And over the last couple of years, since we really started this increased awareness about creatine and health, sales worldwide have doubled to the point where Allschem, the leading manufacturer of creatine in Germany, had to start a second plant. And there's actually a worldwide shortage on creatine availability that people are starting to put it into a lot more type of supplements for general health, and really looking at things like recovery and pre-workout supplements and things to just promote general health as you age. And so we're going to talk about today what we know about creatine as a sports supplement, but I really want to focus in on the role on how creatine is expanded into the health market. And so really, how is this transition from a sports supplement to a health-related supplement that now has applications from the 3rd trimester pregnancy all the way to the elderly individual that can benefit from creatine in certain health and disease conditions. So a little bit of background, you already know, anybody knows sport nutrition knows creatine is one of the most popular nutritional dietary supplements out there. It has extensive body of literature. There are well over 1,500 clinical trials that have been conducted, short-term, long-term, many studies on health and safety. And the data shows that if you take extra creatine in your diet, you will load more creatine in the muscle. And this will allow for more phosphocreatine to be available for energy, for high-intensity exercise and performance. And if you take creatine, you get benefits like greater recovery and more glycogen storage and better thermoregulation and some rehabilitative effects. There's even evidence to suggest that there's a lessening of severity of things like concussion or traumatic brain injury, which we'll touch into a number of areas. So that's just the general background. And so if you look at creatine, you can get it from your diet, or you can get it from the natural synthesis capabilities that the body has. About half of your creatine that you have for daily needs is synthesized through a creatine pathway that involves the combination of L-arginine, ornithine, and glycine to form guanosine acid. And that then is methylated to form creatine, and then that creatine is available in the cell for phosphocreatine for energy. And so this can be done not only in muscle, but kidney, liver, pancreas, and even the brain. There are different transporters and different creatine kinases that all involve in the transportation, utilization of creatine, and synthesizing phosphocreatine and resynthesizing ATP that are being sent by the body to increase the need. And so that's the basic synthesis. And so if you take a person, 95% of most creatine stored in the muscle. That's why a lot of the initial studies looked at performance and muscular adaptations. About 2/3 of that is stored as phosphocreatine, and the other third is free creatine that's available to be bound to phosphates and form phosphocreatine and recycled for the ATP-PC system. As I mentioned, you have a half of your daily need for creatine from the diet, depending on what type of diet that you have, and that's generally recommended to be at least 1 gram, maybe 2 grams per day from your diet to offset what the body can synthesize. And so most of that comes from things like meat and fish, and we'll see in a minute about the content. And so when you consume a meal that contains creatine, for example, in orange here is 2 grams of creatine consumed with meat. You typically get an increase in creatine in the blood that is sustained for 3 or 4 hours, and that's enough to be able to increase absorption of creatine through creatine transporters into tissues that need the creatine, and then the creatine is available to form with phosphates to form phosphocreatine. If you compare that to putting 2 grams of creatine monohydrate in fluid, you get a little bit higher peak from creatine monohydrate, but you still see this effect for about an hour or so peaks, and about 2-3 hours later, it's sustained. This is the same whether you have it in solution or in candy or in gels. There are often different type of supplements. Gummy forms of creatine now are popular, for example. And the 5-gram dosage comes from initial studies by Roger Harris that showed that the optimal level to peak in the blood to really push creatine through transporters into tissue is about 5 grams. And if you can see, 5 grams will get about an increase to 800 micromolars per liter compared to food, which is about 200 to 300. And that will stay elevated for about 4 hours. Thus, we recommend 4 doses of 5 grams a day to maximize absorption into muscle. And those studies have been done to show that. So that's an impact. Now, there's lots of information about creatine in different forms. If you look at Instagram, there's one now on creatine HCl that's being pushed. It's supposed to be better than creatine monohydrate and have no side effects, and it's a bunch of garbage. Okay, so here's what you need to know. Creatine can convert to creatinine. It's very stable in creatine monohydrate form. And if you look at the diagram here, if you put creatine monohydrate in water and had a neutral pH, it'll take about 3 to 4 days, and you might see a 5 to 10, 20% drop off in the creatine amount in that fluid based on the conversion to creatinine. So a lot of people who are trying to get market share will say, oh, it doesn't convert to creatinine. Well, here's the problem. When you consume creatine monohydrate in the body, it gets to the stomach, and the hydrochloric acid stomach and the pH in the stomach is well below 2.5. Once you're below 2.5 pH, creatine does not convert to creatinine at all. The same thing when you get a pH above 12. And so when you consume creatine monohydrate powder, it's nearly 100% bioavailable because it does not degrade into creatinine. It is either absorbed into tissue that needs it or is excreted in the urine. In fact, we do studies where we can actually measure creatine retention based on measuring how much creatine went in and how much is urinated out. And the difference is basically what the body retained. So with that understanding, we know that if you take 3 to 4 doses a day of about 5 grams per dose, and you load what we talk about loading, that this will increase creatine about 20 to 40% within 5 to 7 days. And there's some that have suggested that 0.3 grams per kg is probably a better way to gauge this depending on different sizes. And there's some also, if you take 28 days of 3 to 5 grams of creatine, you'll get about 80% retention after a whole month. And so that's a kind of a low dose protocol. And so usually we'll recommend loading and maintaining and versus the low dose, although health proponents suggest you should probably take 3 grams per day throughout, we'll talk about. And it takes about 4 to 6 weeks after taking creatine and the stores of creatine elevated for them to dissipate back down to normal. So it takes time after you've loaded to really see a drop in creatine. Now, if you took a person on a normal meat-eating type of diet, they have about a 100 millimole per kg dry weight muscle concentration of creatine. If you creatine load 20 grams a day for 5 to 7 days, you'll add about 20 to 40% creatine to that pool. That means you have more phosphocreatine in the muscle, more energy for explosive activities. And if you take it with carbohydrate or carbohydrate and protein, you'll get even a greater retention. We've often talked about this upper limit of 160 in the literature. And on average, that's about right. But there are individuals that can store 200, 220 millimoles per kg dry weight. So we're learning more that certain tissues might have higher levels and withstand more uptake of creatine. And so generally, if you consume more creatine in your diet and load, you tend to have a 20 to 40% increase. Note that in vegetarians, we typically don't get as much meat and fish in the diet that contains high levels of creatine. And in the elderly, because of digestion issues and maybe not consuming as much protein, meats and fishes, type of foods, they typically have a lower level of creatine. And there's actually some data showing that vegetarians respond better to creatine supplementation, and probably more important for them and elderly to get the stores back up to normal. So this is kind of like glycogen loading. If I have a long race and I start preparing to go for a marathon race or a triathlon, and I increase my carbohydrate intake before the competition, I load the muscle up as much glycogen as possible and liver with glycogen, I will last longer. The same philosophy is with creatine loading, is if I load the muscle up with more phosphocreatine, with creatine supplementation, I can therefore have more energy available to do sprints, recover from sprint to sprint, and result in a better quality of training. So that's the basic philosophy. Now, a couple years ago, we did an update on our bioavailability paper, and there's only one creatine form, creatine monohydrate, that has been shown consistently in the literature. 95% of all studies we've done on creatine monohydrate. And this is the only form of creatine that has worldwide approval to be sold as a dietary supplement. And there are a few things out there that have a little bit of evidence to show some efficacy, but notice it takes more creatine of those sources to equal the same dosage of creatine monohydrate. So we typically think these are less effective because it would take more dosage to equal the impact of creatine monohydrate. And none of these studies show greater uptake, even though you hear a lot of media and advertising saying these are better. None of these have been shown to have any beneficial effect, and none of these shown to have better training adaptation effects. So creatine monohydrate is still the king of the mountain. The other ones seem to have a little bit of effect, and there's a whole bunch of things that studies simply show do not work. So this is generally recognized as safe. It's approved by FDA. It's approved to even put into food additives, not only in human food, but it's also quantity of acetic acids put into feed and other things for animals, and to try to increase creatine and availability for them. So creatine monohydrate is the best one. So what do we do? What do we know? In 2017, we did our second position stand on creatine supplementation, and here's the take home. It's the most effective ergogenic aid to increase strength, power, high-intensity exercise performance, and training adaptations for power-type athletes. It's not only safe, but has been used in large content in clinical populations in dosages up to 30 grams per day for 5 years. Our initial studies actually were 15, then 20, then 25 grams per day for up to 3 months in athletes to try to see if there's a benefit. And so there's lots of safety data. Next thing, if you are a younger athlete, some of the initial studies on safety of creatine are actually in clinical populations in kids. And when you look at the relative intake, they are relatively high. So our position is, as long as the adolescent athlete knows what creatine is eating a good diet, training well, and doing other things properly, then creatine can be something to consider to improve their performance as well. And we'll give you some data to support that in a minute. So what else? Warnings about creatine, sometimes on labels, is generally for legal interest, has no data to support the need for. Right now, creatine monohydrate is the most extensively studied and best evidence to show clinical safety and efficacy. If you add carbohydrate and creatine, as I mentioned, you'll get a little bit better retention of creatine, and you may also get some greater advantage of glycogen loading effects from taking creatine as well as the carbohydrate. The best way to load and get creatine stores is to load with that 4 times 5 gram dosage per day, or 0.3 grams per kg per day for 5 to 7 days. And then it takes about 3 to 5 grams thereafter to maintain, except if you're a large athlete. If you're a larger athlete, we actually have data in football players. Many of the average football players was about 100 kilos and up to 140 kilos. They need about 10 grams per day to be able to maintain their creatine store. So in larger athletes, we actually recommend a little bit more. In clinical populations, which we're going to focus on, studies have shown really high intakes for a very long period of time. Equivalent dosages of 21 to 56 grams per day in 70 kg individual equivalents, clinically for years without any side effects associated with that. And so we in 2017 said we need to do more study on the health effects, and there's beginning to see some evidence in clinical populations of benefit. And so this prompted us a couple of years ago to launch a creatine health disease initiative with the support of AllsChem, and Jeff Stout and I sponsored a special issue on creatine for health and nutrients that then wrote a seminal paper that's been cited hundreds of times so far. And we talked about all the different roles of creatine in health and disease that have been studied, or at least been started to study or speculated and theorized that there may be benefit. And we'll show you some examples. And we have a great website called creatineforhealth.com where you can see all the papers that are published in this series, download the book that came with it, and also see all the presentations of the 2022 conference that was done, all available on YouTube, free. Take a look at it if you want to know about creatine and health. So why is creatine important for health? Well, we're going to look at several applications. First, The metabolic basis for creatine health really deals with all the metabolic roles that creatine plays in the body. This diagram from one of our papers in the special issue has little green lights or sparkles. And everywhere you see green is everywhere that creatine plays an important role in metabolic activity and things like mitochondrial function and nerve transmission and energy capabilities and shuttling phosphated and glycolytic intermediates, muscle protein processes and contraction, neural pumping. And so when there are deficiencies or mitochondrial dysfunction, they alter the metabolic activity, and this is where creatine plays an important role, as we'll see in a minute. So let's take a look at this. We'll go from a spectrum of infants all the way to elderly, and then some disease, and then we'll talk about the dietary influence of creatine on health. And so the first one we'll talk about is work from Australia, from Stacey Ellery Lab, and they've been doing lots of studies on creatine in pregnancy. Mothers who are pregnant have lower creatine stores because the baby is actually pulling creatine out to develop and have normal development and maturation during the pregnancy, particularly during the third trimester. And when there's asphyxia that occurs during childbirth, like a cord wrapped around the neck of the baby, the blue baby, they found in animals that if they creatine-loaded animals before they had those type of asphyxia-related births in the animals, that the survival rate was markedly improved and the amount of brain damage was markedly reduced by having these animals fed. And so this got them to take a look at lots of what happens to creatine levels in tissues, in animals and humans as people go through maturation. And we know now that creatine is very involved in the reproductive health of women. Everything from the endometrium and follicular fluid, placenta has a high concentration of creatine in it. And so that during metabolism and pregnancy, there's a greater dietary need of creatine. So we actually are recommending that third trimester women add creatine to their diet to be able to provide this energy and availability of creatine needed and to reduce the risks associated with asphyxia during childbirth. Interesting. And there's a bunch of new studies coming out on this. This is a new area of creatine application. Next. We've talked about creatine in athletes, and usually we think of college age or older adolescents, high school athletes. But there's been a lot of use of creatine in younger children. And we know that kids who have neuromuscular diseases or creatine synthesis deficiencies, that they benefit from having extra creatine in the diet. There's actually some data will show that indicates that kids with low creatine in their diet have a number of health outcomes that are not beneficial. We'll see that a little bit later. So things like cancer and depression, brain injuries, spinal cord injuries, orthopedic injuries, bed rest, all have had application, particularly when there's muscle myopathies or muscular dystrophies in kids. And the dosage of these adolescents and children are typically well above loading doses for long periods of time. And so this is some of the interest here. And so we all know of the athletes, even in high school athletes, they can see benefit. But in children, there's been a lot of interest in use of creatine clinically. Then we know about the performance effects. And this paper we did breaks down the types of performances that creatine has been reported to benefit. Strength and power is what we typically think of creatine, but there's also some prolonged high-intensity exercise, endurance exercise, agility, sprint performance, jump. All these type of competitive athletes have been studied and shown benefit with creatine. And there's even data showing faster recovery, less muscle trauma, less muscle soreness, better recovery when you have creatine. So from a performance perspective, there's lots of data supporting efficacy, and Ben Wax did a nice job summarizing this. The really hot areas now are women's health. We now know that as women typically don't synthesize as much creatine in part because of body mass and muscle mass differences, etc. And so they tend to be a little bit lower on creatine content than male counterparts. We know that as you go through the menstrual cycle, there are changes to creatine kinase, PCR, creatine monohydrate might affect and improve that and lessen the effects on menses and pregnancy, postpartum, menopause. All these things are being studied, and Abby Smith-Ryan's leading that charge at North Carolina. We know that premenopausal, perimenopause, postmenopause, there may be some benefit on things like bone and preventing fat accumulation and helping keep lean muscle mass. There's even data in women on cognition that we'll talk a little bit more about in a second. So the whole aspect on women's health, Abby's now doing studies where they're looking at providing creatine at different phases during the menstrual cycle to see if they can optimize not only training, but health outcomes. Another big area is creatine and aging. As you get older, you lose muscle, you gain fat, you have less strength, and you typically lose bone and lots of cognitive function declines. And so we now know that when you give creatine to older individuals, especially when it's combined with an exercise program that involves resistance training, you get stronger individuals, you get more muscle mass, you tend to see a little bit more fat loss. Bone mass has actually been increased in studies up to 2 years. Performance is improved, and there's even data on cognition that's improved in elderly. And so populations that are osteosarcopenic, sarcopenic obesity, frail, cachexia are now being looked at as a population where it may benefit from not only protein intake and resistance training, but also creatine supplementation in addition to that. And Darren Canada's group has done a wonderful job looking at that. Then there's a whole area of research now looking at creatine in the brain. And this research started with observations that creatine is related to lack of creatine in the diet is related to depression, and that if you give creatine, you actually can increase brain creatine content and phosphocreatine content, and this is associated with better cognition. And so there's also evidence that if you get injury to the brain, if you have creatine in the brain at a higher concentration in animals where they cause concussions or spinal cord injury or stroke or some type of brain damage, that the individual or the animal that is fed creatine in their diet doesn't have as much severity of trauma due to the insult. And so there's a lot of interest now how we can increase not only your muscle creatine, but optimize creatine uptake in the brain and whether that affects function. And there's a number of studies show that if you give creatine loading in elderly, their cognitive functions improve. Your creatine can increase your brain. If you are sleep deprived, it may affect your ability to think with creatine. And we're doing lots of studies now in interest of how creatine can reduce the severity of concussion and traumatic brain injury, and even treatment of CTE in athletes and military. And we're actually working to try to get some large-scale studies going with that. And so a whole host of things on brain and creatine function. What else? There are studies in heart disease that if you provide creatine, the heart can function better, contract more stronger, and have less arrhythmias. And so they have actually done studies where they've induced heart disease and stroke and heart attacks. And they basically found in heart failure models that providing creatine or creatine feeding helps improve the heart's ability to withstand ischemic events. And so maybe this could be something for heart patients to take to prevent or reduce the potential of problems associated with angina and other type of events. So this is another area of real interest now with creatine. There's actually data now in vascular health that the endothelial cells are dependent on creatine, and the ability to have creatine can affect the nitric oxide production and the ability for the vascular bed to respond to pressure and oxidative stress and other stressors that affect it. And so there's some thought that maybe creatine can help with vascular smooth muscle compliance. And there's also evidence in a few studies showing lower cholesterol. And so there's some interest in the general heart benefits and vascular benefits from creatine supplementation. Say, okay, well, wow, I have no idea that creatine did all those health things. What else? They've actually now done studies in certain diseases to see if creatine supplementation can help mediate or manage the disease or progression disease or reduce the need for medications. So, for example, kids that are born with creatine transport deficiencies or creatine synthesis deficiencies, they don't have those enzymes to produce creatine as well, or they can't take the creatine up in the cell, that they have been given very large doses, 0.3 to 0.8 grams per kg per day, to try to help reduce this. And when they identify infants that have creatine synthesis deficiencies, they typically have very poor mental and physical development in the first few years of life. It's noticed. They identify the brain deficiency, in particular the low levels in the brain. They start treating these kids, and their motor development is much greater and much more on a normal path once they identify this. So there's a lot of interest initially, and their studies have gone on for years where they've given these kids with certain deficiencies creatine to try to help prevent and improve function. We did a paper on mitochondrial dysfunction. When you have things that reduce the mitochondria's ability to function, there's a greater need to produce energy anaerobically. And when you handle ischemic events, if you have more phosphocreatine in the cell, it allows the cell to be able to handle those ischemic events with less damage. And so there's a whole host of mitochondrial deficiencies that are typically associated with poor creatine content, and by reversing that, we see some benefits in these type of populations to improve mitochondrial activity and function. There's been a lot of interest in, well, if creatine helps training and strength and muscle as you do conditioning, what happens if you get injured? Does it facilitate a faster recovery? And generally the studies show that if it's a muscle-based injury, it seems to allow for greater recovery from exercise, spinal cord injury, arthritic diseases, and even muscular dystrophies. The evidence is pretty strong that creatine can benefit those type of populations. In the diagram, you can see which ones these are. And then possibly affect, I mean, it's a little bit more equivocal. These are muscle and some nerve intervention type things. There are studies showing injury and mobilization, less atrophy, for example. COPD patients have improved lung function. A number of different types of clinical conditions may have an effect, and it's less likely to affect, probably not affect, in the damage to nerve type of diseases like ALS or multiple sclerosis or Parkinson's. But these studies have been looked at for the role of creatine. What else? If you're diabetic and do exercise that includes resistance training, you have a greater ability to manage glucose better. And the diagram kind of shows you that it improves insulin sensitivity, it improves the ability to, through AMK, to get GLUT4 and be able to take up glucose in the cell. And so you're less dependent on things like insulin or glucophage or things, medicines that may help you manage your glucose. So the initial studies show some promise in people with diabetes who are doing exercise. There's some fascinating data that of Kristen Dresser's lab at Creighton showing an immune response, that in some autoimmune deficiencies, creatine is a major source of energy, phosphocreatine, to help this immune cell handle immune challenges. And so these changes seem to improve immunity in certain populations. And part of that is because it takes away the inflammatory process that's associated with some of these diseases, and therefore has some potential effects, not only in autoimmune diseases, but even some infectious disease. In fact, there's data now in cancer that from Lily Yang's lab in UCLA and others that show there are certain cancers that creatine, a lack of creatine, makes it easier for the tumor to grow. And by providing creatine, it actually retards or slows down tumor growth in certain types of cancer. So there's a whole interest in whether creatine availability and phosphocreatine can help offset some of these potential cancer and tumor growth and help manage in certain types of cancer. So very interesting type of work there. There's even studies in inflammatory bowel disease. Creatine is a player involved in the uptake of nutrients in the intestinal epithelia. And because of that, it affects your ability to absorb nutrients effectively. And there's some evidence that irritable bowel syndrome, for example, is related to a lack of creatine and ability to manage and process these nutrients as they're trying to be absorbed. And there are studies underway that are trying to look at, is creatine a way to prevent or improve outcomes? And there's a couple studies initially that are suggesting some potential benefit on inflammatory bowel disease. Wow. Some of the really cool stuff is that there were some studies out of Utah with Perry Renshaw that showed that depressed individuals that were suicidal and non-responsive to medications seemed to have low creatine availability. And then they did a study where they looked at people with depression seemed to have lower creatine stores. And therefore, they postulated that if you provided creatine, you can then reduce depression. And they actually have some studies where they combine creatine with acetylcholine and fish oil and show a lessening effect of depression, a lower propensity or interest in things like suicide. Fascinating area on brain effects. The last one I'll mention is post-viral fatigue and long COVID. And this is some studies out of Serbia with Serge Osijic, and they found that people who have chronic fatigue typically have symptoms that creatine might be able to benefit. And there's actually been some studies now that show that people with long COVID have lower creatine content in the brain. And when they give creatine to people, since our last international conference in 22, and seeing that study by Renshaw, looking at the health implications of dietary availability of creatine, we talked about the need to do some of these studies. Let's look at NHANES database. So here's some. Serge Osijic's done several of these. And the first one was they found that kids who had lower creatine in their diet had less gain in height, stature, less muscle, or less weight, and a lower BMI, suggesting that lack of availability of creatine may affect normal maturation. They then said, well, let's look at body composition of kids. And they found that kids with lower creatine content in their diet typically had less muscle mass, greater fat concentration, and less bone mineral content than kids who were getting normal amounts of creatine in a diet. And they defined this generally at least 1 gram per kg per day. They then said, well, let's take a look at women. And they did a large study and found that women with higher or recommended amounts of creatine in their diet had lower risks of irregular menstrual cycle, irregular periods, obstetric conditions, and pelvic pathologies. So there's a definite women's health impact on lower creatine versus higher creatine in the diet. They then said, well, let's look at older people. And they did a large database again, looking at older individuals, and found that people who were older, above 60, had lower creatine in the diet, had negative correlations on cognitive function, meaning that the more creatine you had in your diet, the better your cognitive function as you were older, above 60. They then did studies where they did creatine and looked at older men and women and looked at general health, and they found that people with low creatine intake in the diet had a 2.6 times higher risk to angina pectoris, had a 2.6 times higher risk of liver conditions compared to those who had normal creatine. So there seems to be some effect on chronic disease as well. What else has been done? There's studies showing that if you have people who have higher creatine content, does not have any association with kidney abnormalities, which is some of the thought on high protein diets maybe. It may be detrimental. Well, creatine doesn't seem to have any adverse effect there. There have been studies showing that if you have a higher creatine intake, there was no liver problems for liver fibrosis, cirrhosis, etc., compared to those who are lower. And they found, interestingly, that people with higher creatine content had less or higher neurofilament light chain, which is a neuronal damage type marker, and basically suggesting some higher creatine dietary effect on reducing damage to nerves as you age. Interesting. What else? There's a last study we mentioned is average intake of creatine was lower in kids and infants than expected. Okay. And there's even data suggesting that pregnant women have lower than optimal creatine intake. So, wow. How do you summarize this? You got creatine? Is creatine in your diet? Is there enough creatine in your diet? And so here's a summary. The benefits of creatine go well beyond what we thought about performance and muscle and training adaptations, lifting more weights, and things that we did our initial studies on anaerobic power and strength. There are a lot more evidence that there's therapeutic benefits throughout the lifespan and in clinical populations where creatine, phosphocreatine may play a role in the disease management or pathology. Therefore, we recommend that everybody get at least 2 to 3 grams of creatine in their diet. Now, if you don't like to eat lots of meat, that means having a little bit of supplemental creatine. 1 little teaspoon is about 5 grams. It's very inexpensive, but there seems to be a lot of health benefits as you age. Some high-risk disease populations may need more. And for brain, for example, our current study on brain and cognition and older, we're actually giving 10 grams a day, 2 times 5 grams for 12 weeks. To see if we can get a higher brain content and also some cognition effects from that. And there's a lot of opportunity to research in health as well as how creatine can be applied and implemented for just general population benefit over time. So the last thing I'll mention, our next creatine conference is this spring in Munich. It'll be available in person as well as online like we did last time. It will have major themes around impact of creatine on aging, women's health, disease management, metabolism, cognition, and exercise, sport, and safety. We'll have abstracts. We're going to have presentations. There'll be awards for students. If you're interested, take a look at that. Go to creatineforhealth.com right here, and you'll learn more about that. But what I want to leave you with is creatine is more than a sports supplement. It's a health supplement. And what started with just looking at performance enhancement is a great example of how sport nutrition has now transited into general health and even potential for disease management and as adjunctive therapy to other type of clinical management of people with disease. So with that, I'm about out of time, so let me go ahead and finish it, open it up for questions.
फासले क्यों रहे तुझसे दूर क्यों हुए निकली क्यों तो बेपरवाह वास्ते टूटते अधूरे से ही रह गए हो गए खुद से ही जुदा राहों पे चलते थे बिछड़ गए जो साथ थे कहने को और कुछ ना रहा झुका नहीं मेरे दिल को थी खबर नहीं चलती रही ये जिंदगी जल गया पिघल गया था तेरे प्यार का नशा और ना रहा कोई आसरा खो गया उन रास्तों पे था मैं अकेला मैं तन्हा मैं तेरा अपना रहा जो तेरा कभी था मैं तेरा दुनिया की प्यास में तू है दोस्त हमको भूल गई खुद के सपनों में